Всех приветствую на 8-м этапе, который мы проводим. Вот. Рад видеть и постоянных участников, и вижу, новые лица сегодня появились. Вот. Ну, сегодня у нас очень интересный гость. Я даже не буду представлять, я думаю, Саша сам о себе расскажет, если кто-то вдруг не знает. Вот. Ну, давайте тогда начинать. Саша,
Здравствуйте, добрый вечер. Я буду по-английски докладывать, потому что так по-русски общаться на общие темы нелегко, относительно, а про компьютер рассказывать сложнее. Но если вам удобнее задавать вопросы по-русски или в конце просто подойти поговорить, то, пожалуйста, без проблем. So this is a talk about PerfView, which is one of my favorite tools in the world. It is very ugly and hard to use.
Yes.
But it's still my favorite tool in the world because it can do so many things on Windows, because it is free, because it's actually open source now, and because you can put it in your production systems very easily. It's just one executable that you can very easily copy between machines. And it gives you an unprecedented amount of information about what your application is doing, what your whole system is doing, and it's based on the very powerful ETW framework, Event Tracing for Windows. And so the plan for this talk is generally to talk a little about ETW itself, and then spend most of my time just showing you examples and demos of PerfView. It should take anywhere between 1 and 1.5 hours, probably around 75 minutes. If you have any questions, please ask them. And you can also, of course, ask questions at the end if you prefer. Just 2 words about myself. My name is Sasha Gольdштейn. I work for an Israeli training and consulting company called Sela. And this is most of my work. I guess about 60% of it is debugging and production performance investigations for customers. I also do training and speaking like this, but most of my work is just solving other people's problems, basically. And PerfView helps me a lot, and so I hope it would be useful for you as well. So this is this spectrum I like to show of different performance-related activities that you might be doing in your project, in your software project, in your work. And so it starts up top with performance metrics and simulations, things that you should be doing before you write any code, before you have a project. Sometimes there is a project and then you start looking for performance metrics. This is also fine, although not ideal. And it can be done on a piece of paper. It can be done in some very smart computer software, but the idea here is just to find the numbers you care about, the metrics that your users care about, the things that you would like to monitor, to get alerts about. This is not what PerfView is really good with, so just managing expectations. Then we have development time profiling, which is also a pretty important performance-related task. And as developers, I assume most of you are developers, this is where we spend some time, hopefully, trying to improve performance in development before any customers or QA ever see the product. This is something PerfView can help us with, but there are better tools, I think. Most of them commercial, like the JetBrains tools, Redgate tools. There's a lot of tools really well suited for development time. You can install them on your laptop or your desktop and use them with Visual Studio even. But in production, not really. Not so much. A lot of these tools, you can't put them in production. A lot of them are too heavy to be put in production. And a lot of them require licenses which you don't want to pay for each production server. And this is where other tools can be more relevant once you get later in the pipeline and you get to the load testing stage where you have actual semi-production instances where you are doing performance testing and load testing, and you probably don't put profilers there, although some people do. And even more, once you actually do get to full production and you have users of some kind working on your system, and on those servers, nobody I know would install something like .trace, well, hopefully. Not because .trace is bad, it's just it's not really a production tool. And this is one place where Purview can help us a lot. Once the system is in production, and we need lightweight tools, we need non-invasive tools, we need tools that you can easily copy between machines and you don't need a license to use, this is where Purview really shines. And one other thing that has to do with continuous monitoring, Purview can also be quite useful for. So that last phase there, once the system is running, and there isn't necessarily a problem yet, but you want to monitor the system, you want to make sure nothing bad happens, this is somewhere that Purview can also help you with. Purview has a bunch of options for running continuously in the background, and only if there's a problem, you would get a more expensive recording of what happened, so you can analyze it later. Most people don't really use it like completely continuously for months at a time. Most people use it maybe for a few days when they know something might be wrong and they want something to run in the background, collect information, so you can analyze when something happens. So in all of these phases, again, different tools are useful, and Purview is mostly relevant for these two phases on the left. So here's just one tiny story to put things in perspective of a production performance investigation we had a while ago, where the source code for the system wasn't actually available to the people who experienced the problem. So it was a project where development was in one continent and very, very far away, and the people actually supporting the system and facing the performance problems were in a different place. And so the problem was that users had issues loading and saving documents in some document management system, and we tried to diagnose what we could, but again, no source code, the system is in production, so we can't run any invasive profilers or any debugging tools or something. And the sad thing is that the best level of information we got was very, very shallow, very, very basic. So after a whole day of investigation, we were able to discover that, well, we were able to find out, let's say, not discover, that the average latency, the average write and read speed for that storage system was 5 milliseconds. It took a whole day to discover, and it wasn't really very useful because an average doesn't mean a lot. It could be a 5 millisecond average, but some operations still time out because they take 5 seconds. Averages are not very good like that. After a lot of additional work, after a lot of additional tools that the consultants who were brought in on this problem ran and used, we were able to get something slightly more detailed, which is per minute averages of the storage system's latency, and the average of averages of those per minute averages was 5 milliseconds. So still no problem, and this is more or less where the budget ran out. And what I say to all of this, and to a lot of stories like this, is just, use a profiler. And a lot of people would reply that you can't use a profiler in production. You can't, what do you want? I'm not going to install .trace or Visual Studio or something like that on my production system. But yes, you can use a profiler in production, it's just not going to be Visual Studio. And so hopefully, if you had this kind of issues in the past where the very basic shallow monitoring tools just don't give you enough information and you need more, then you should know you don't have to go back to development, you don't have to try to reproduce this on your work laptop. You can run a lot of diagnostics tools in production if you're a little bit careful. So again, these are some problems with the traditional profiling tools, which I already mentioned before. Just to reiterate, invasiveness, by which I mean a lot of tools inject themselves into your process, or launch a lot of additional processes which are very heavy, which is not really suitable for production. Overhead is a problem with a lot of tools. with a lot of profilers, which make them unsuitable for production because they will slow down your application too much or slow down your system too much. Trace size is a problem with a lot of tools. So they generate just very big log files, and then they might crash when you try to open them, or they're just too big for your disk and you can't afford that much disk space in production. And of course there's licensing as well. So we don't want to pay for each production server to install profilers on it. So this is where ETW and Purview come in. After this possibly too long introduction, let's get started with the actual tools. So ETW is event tracing for Windows, and it is the magic tool for performance investigations on Windows. It has been around since Windows 2000, and it has probably the worst marketing in the world, because in the last 17 or 18 years since Windows 2000 was released, there are still very few people who have heard about it. There are fewer people who used it, and even fewer people who actually did something useful with the output. And some of the reason for that is that it's not just a little obscure and hidden. Some of the reason is that the tools occasionally are not very user-friendly and don't look very good, and you kind of have to be a performance expert to run them, but not really. So ETW is extremely powerful, and it has been around for a very long time. And it started as a log framework, so that Windows drivers and Windows kernel components could write log messages really fast. So that Microsoft people could investigate issues in production. So that Microsoft people could enable logs on a customer's system and then read those logs really quickly on their system. But since Windows 2000, a few things happened, and ETW usage has exploded all around Windows. It's used not just by drivers in the kernel, it's used by a lot of application-level frameworks like .NET, ASP.NET, TPL, WCF. It's used by databases like SQL Server. It's used by even higher level libraries. And not just .NET languages also. C++ has access to ETW, and other Windows languages have as well. So today, it's definitely not just for Microsoft engineers trying to reproduce driver crashes in Windows. Today, ETW is for everyone. And since Windows XP, actually, there is an API for us to add events to ETW, to write events through that framework as well. But most of us probably are not using it as a log framework. Most of us have some other kinds of log frameworks available. So in this talk, I'm not going to try to convince you to use ETW as your main logging framework. Although maybe we could do a separate talk about that. I'm going to just tell you about some of the useful things you can read from other people's logs, so not yours. So here are some of the main components in ETW, which we're going to look at today. So on the bottom here, we have providers. Providers are just components that write log messages. There's providers all over the system. So again, the .NET runtime itself is a provider, and we will look at some of the .NET events later. Windows itself, the OS kernel, is a provider, and it has a lot of interesting events. And then, again, you have a lot of higher level stuff, ASP.NET, WCF, and so on. So we have providers, and what's interesting about ETW is that all providers, by default, are disabled. So nothing is logged until someone asks for it to be logged. The person asking, the component asking, is called the controller. And so what the controller does is it creates an event tracing session, which is a kernel object, just like a mutex or a process. So it creates an ETW session, and it enables certain providers to write into that session. So you turn on providers and you tell them write to this session or that session. And it's all cross-process, of course. So the provider could be one application and the controller a different application. The provider writes events to the session, and the provider does this using a Windows API. So it's really part of the OS. It's not like something like Log4net, which is a user-level library. ETW is a Windows API implemented in the kernel, which hopefully helps convince you it's fast, or as fast as a logging framework could be. And then the messages you write go into buffers. The buffers are also managed by the kernel. They live in physical memory, locked in memory, so they are not paged out accidentally. And you can configure, if you want, you can configure your session to also write events to a file. But you can also have a session which is only in memory, so you're not paying anything for disk access. So the events are only in memory, and if you run out of space, you can do a cyclic buffer and just get the newest events, which is really useful for continuous production monitoring when you don't want to record anything to disk because it's too slow. So you have controllers and you have providers. Finally, you also have consumers, which can read events. You can read events in real time from the memory buffers, or you can read events from a log file. So your session can write everything to a file, and then you have some kind of tool read from that file and do analysis. This is also very interesting because it means you can process the logs in real time. You don't have to wait for 3 hours for the system to stabilize and then read the whole recording. You can build tools which monitor events in real time and react accordingly. If you're only interested in averages or like alerts or something, you don't need to record anything to a file. You can just build tools that would look at the memory buffer and do whatever you want. So this is just really powerful things ETW has built in, and not a lot of other profiling tools can offer. So here are some interesting providers for us to look at, and they will be the basis for some of the scenarios I will show you soon in the demos. So the first one is a kernel provider called the profile provider or the sample provider. This is a kernel implementation of a timer that fires every millisecond by default. And when that provider fires its event, it will also capture the stack trace of the current CPU. So what's currently running, the current thread that's currently running on the current CPU. If you have multiple CPUs, multiple cores, it captures on all cores. So every millisecond, you get a picture of what your threads are doing. You can then aggregate this information and get a report that tells you this function cost me 80%, that function cost me 15%, and so on. It's just samples, right? So it's statistical. You get snapshots of what the system was doing, but it's relatively accurate. If you have enough samples, the error goes down. So the more samples you have, the more accurate it is. This is how most profilers today do CPU profiling. Even the ones that don't admit they use ETW, they probably use ETW. So they use this technique of sampling every millisecond. The interval is configurable. So if every millisecond is too often and slows your system down, you can sample less. You can do like every 10 milliseconds, 20 milliseconds, whatever you prefer. Then we have the CLR providers, and there are many of them. I just put here the GC and the sample allocation provider. These allow you to trace garbage collections as they happen in your process, and a lot of statistics about them, which I'll show you later, like the duration of the GC, how long it took, how much memory was actually cleaned, so was it a good GC or not. So a bunch of stuff about the collection itself. And the allocation provider lets you know what kind of objects you're allocating. So you can get a summary of which allocations your application is performing so that you have less GC. If you have too much GC, you're probably allocating too much, so you can reduce allocations by understanding where they're coming from. Again, this is something that a lot of profilers use, even if they don't say they use the ETW events, they probably use them because it's just a very easy way of tracing allocations. A couple more examples. In the kernel again, we have the context switch provider, which lets you know whenever the system switches from one thread to another. Just the standard context switch definition. This is generally not really interesting, but if you think about it, every time there is a context switch, it could be for an interesting reason. Like I could be switching out of the CPU because I just called some blocking API, like sleep or wait or disk access or something like that. So if I trace all the context switches, both in and out, then I can tell you all the blocking work your threads are doing. Whenever your thread is doing like I/O, I can tell you this I/O took 30 milliseconds. If your thread is trying to wait for a lock and the lock was taken, then the thread is going to wait. I can tell you this lock caused you to wait for 150 milliseconds. So you can do really, really accurate tracing of any weights in your code by using that provider. And finally, we have, for example, the file I/O provider, which just gives you an event for each file access. So you can find slow file accesses in your code. It's interesting for startup performance, for example. When you have an application starting up, reading lots of files is probably slowing you down. So you can see which files you're accessing and optimize accordingly. This is maybe 0.01% of what you can do with ETW. Obviously, there are a lot of interesting events, and there are a lot of scenarios in which they are useful. Sometimes they will be a provider that you only use once in your career, but that one time was really a lifesaver, and you couldn't solve the problem any other way. And really, it's surprising how many things in Windows have providers writing to ETW. You just have to find them, and I'll show you how to get a list of them. So suppose you make a recording of ETW events, and I'll show you how to do that as well using PerfView. A recording has a huge list of events. You can convert it to Excel or CSV or whatever you prefer. It's still going to be probably millions of events if you recorded something interesting enough. So clearly, it's useless without some additional processing, without a tool that can aggregate this, visualize this somehow. It's kind of like a big data problem. It's not really very big data, but it's enough data so you can't really look at the file by hand and see the interesting thing. You need some kind of tool to do that for you. And PerfView tries to be that tool. PerfView is now an open source project. Previously it was just a free tool but not open source. It was developed by basically one person. His name is Vance Morrison, and he's a performance architect on the .NET team. He's been working on .NET performance and .NET related stuff probably since the beginning, more or less. He is a very quiet person. He doesn't speak at conferences. He recorded a few videos about PerfView, but I think that's more or less his entire public presence. And it's a very powerful thing he built, but because it's just one person, and because he has no designer, and because he has no requirements, he's basically doing whatever he wants. There are some quirks, there are some things to learn about using PerfView. There has been some improvement over the years, I think. And now that PerfView is open source, there are more people contributing. But the code base is also not very easy. If you read any of it, it will take some time to recover. It's no, really, but it's definitely getting better. Now, PerfView has documentation built in. There are those videos that Vance recorded a while ago. I have a book chapter, but generally there's not a lot of material about PerfView because it's not a commercial product, and most people using it are seen as those crazy experts who can manage this UI. But it's really not that hard. This is an example of what I'm talking about. This is the main PerfView collection dialog, where you tell PerfView which events to record. So you can understand why some people don't like it. There's a lot of checkboxes, and it's all very gray and ugly. I'll show you a couple of examples. So let's see. I want to start in general by using PerfView to do CPU profiling. But before I go there, I just want to show you a couple of things about the UI, and also how to discover additional events to record. So how to discover additional providers, which I didn't tell you about. So what do you do when you're on your own? So first of all, this is the PerfView main window, and all these blue links you see, you don't have to see the text, just you see the colors. All these blue links are real links. If you click, it will open documentation. For example, here it opens the help, and you can find out about the thing that you clicked on. It's not super great, but it's definitely something. Now, PerfView has a very simple menu system with an ability to open an existing trace, or to collect events, or to run a command and collect events. So these are more or less the general options you have here. So again, the only difference between run and collect, run will launch a program and trace it, and collect will just collect data without launching anything, just collect system-wide. So here's what the collection dialog looks like. And this is just the standard part. There's an advanced option. But generally, you provide the data file that you want to record into. You provide some simple configuration here, like do you want to zip the whole thing after recording, really simple things. In the advanced section, you have a large selection of things to record. So all this really is just you saying, I want this to be recorded, I don't want it to be recorded. There's some defaults that Purview will use if you don't specify anything, which Vance thinks are good for everybody. But if you want, to customize, you open the advanced options. And if you look here to the right, there's a provider browser. And here's what the provider browser looks like. Again, you don't have to be able to read all the text, just see the whole thing. So this gives you a list of all the ETW providers on your system. And currently, it's a global list, which is just over here. So all of these things are ETW providers I have on my system. A lot of them are from Microsoft, but also some third parties. And you can also click a process. Like, let's click, let's find here the Visual Studio process. And then you can see the providers specifically in the Visual Studio process, which is also great if you have some third-party application and you're wondering, does it have any ETW events I might care about for monitoring? So for example, Deven, Visual Studio, has of course the obvious .NET runtime provider, for example, which every .NET application has, but it also has some of its own stuff, I think. Well, no, actually these ones are from Windows, but Microsoft Windows application experience, that kind of thing. I also have another Visual Studio. This one has some more, actually, some more providers. So this is just how you discover, what the available things are for you to record. I am not going to talk about this anymore. I'll just show you scenarios of the, default behavior. But you should know that in some cases there's a surprising amount of information you can get from just looking at an application's ETW events. And in some cases it's not even documented, but you can record and then look at the events and discover new interesting things. Kind of like running in a debugger and seeing the trace messages. Okay, so do some CPU profiling. I have this little directory here with examples that I use in my training courses, and I can share with you the repository later. So this is one of those examples. It's called Stupid Notepad. It's a very, very stupid notepad, but specifically it also has a performance problem. So let's see. I am typing something. Hello, this is a nice place to be. I like it here. The weather is not really that great compared to where I come from. Anyway, so you could see, I guess, while I was typing, there were a few icky delays. So I was not touching the keyboard anymore, and characters were just appearing, and it's not because I typed that fast, it's because there are lags in the application. Now this could be happening to a poor user in production, and instead of trying to reproduce this on your system, you can just tell your user to run Purview. But seriously, actually you can, because Purview has command line options. So you can tell your user, here's a batch script that I want you to run, which will run Purview and do everything in the background. But suppose you can actually convince your user to run Purview. So let's see what it looks like. I'm going to do collect. Let me zoom in a little. Collect. And now let's see. I don't need a lot of stuff here. So just looking at the events here, I don't need .NET allocation events. I don't need this. yeah, CPU samples is something I definitely need because I want to see the CPU behavior of this application. Thread time here is an interesting checkbox. It traces context switches, so I can also see blocked time. But let's not record it for now. Let's look just at the CPU behavior. Yeah, that should be fine. I also collect some .NET events as well. And then I click Start Collection here. And it starts recording. And I go back to this stupid notepad, and I will type some more text. A. Yeah, I got tired of typing. Okay, so occasionally there are those real annoying delays. And I wonder what the application is doing during these annoying delays. Right, let's click Stop Collection. And then go back to the Purview window. This is what Purview generated. It's an ETL file. And ETL stands for Event Trace Log. It has your events inside. If we look at the trace info report here, it tells me my OS, and down here, it tells me the total number of events that got collected. So 22,000 events. It's really not a lot. You might be thinking it's a lot, but traces with millions of events are completely standard and nothing to worry about. Anyway, so we have this recording. To understand the CPU behavior of our application, we have the CPU stacks window. So I double-click CPU stacks, and then I need to choose a process. As you can see, I collected stuff for all the processes on the system. My process specifically is here, and Purview helpfully tells me this process had 3.3 seconds of CPU time, which is more than anything else. So let's take a look. Then Purview shows me this window, which is called, I think internally it's called the stack viewer, because it's used for looking at call stacks. It's got a lot of different functionality, as usual, all on a beautiful gray background with unaligned text boxes. It's really powerful, the stuff you can do up here, but it doesn't matter right now. The important parts are down here. So this table here shows me the hottest functions, CPU-wise, in my application. And it shows here the percentage of time I spent in that function. So you can see here, for example, I spent 58% of my CPU time in a function called interlocked compare exchange. And I spent 38% of my time in a function called spell check service check spelling. So that already gives me something. But probably just the function names are not enough. You want to know what called them, how I got there. So there are, of course, additional views. Like we have this call tree view over here. So let's go there. The call tree shows me all my threads. And in this case, there's just one thread. And then I can expand that thread to see what it was doing. Now you expand the tree by clicking the checkbox. I don't know why, but that's what you do. I think the tree control was something Vance learned about a bit later in life. No, I think really it has to do with performance. Populating a tree with all this data would be too expensive, and using a virtualized tree is too hard. So it's just a list, you know. Anyway, so this tells me, you know, the path from main all the way to functions taking lots of CPU here, which are compare exchange and check spelling. Okay, I have the same percentage points here, and the function that called them is this one here, main text key press, right? I'm not sure if you can all see. I'll zoom in just a tiny bit more. So this is a function in my form. Yes, it's a WinForms application. I'm sorry. It's a function in my form that gets called for each key press. Okay, and so we see that this function is not like immediately returning. It's actually doing some CPU work, which could explain the phenomenon we're seeing, where the GUI thread is not responding very well, and I have this latency issue. I don't know if that's the problem, but you know, I just showed you how you can profile the CPU usage of a process. In this case, this GUI process, but the same thing, of course, works for any kind of process. Now, there are a lot of things here that make the output as compact and simple as it is, because there are a lot more functions on the way from main to here. But they all got conveniently collapsed and folded away, so you don't have to see them. And this is all controllable by these settings up top. And Purview has some defaults, but sometimes they will not work for you so well. And this is where you want to read about the different features here. For example, if I disable grouping, you will see how bad it really is, that stack. This is not all of it, right? And you see there's some Windows Forms stuff here, and there are some Win32 functions here, and there are some more Windows Forms, and we're nowhere close to that function I originally showed you. So all of this collapsing is super important for a performance tool. And some profilers do it quite well. Purview has its own idea of how to do it. I imagined the question, okay. So that was Purview's CPU stacks report, which shows you where the CPU time is going in your application. I'll show you a couple more features in different scenarios, but this is one of the simple things. And it's deliberately simple because it's very common. Like, a lot of us will do this many times once you get used to Purview. Collect, open the CPU stacks, see what the hottest functions are, improve, hopefully, do it again. And that's relatively easy and well documented. Relatively well documented. By the way, this whole tree with the checkboxes is just one way of looking at a lot of call stacks and trying to understand where most of your time is. There are other visualizations. Purview specifically has only this tree. But this thing on the right that you see here, this is something you won't see on Windows very often, but in other OSs it's quite common. This is called a flame graph. And it's another way of visualizing lots of stacks and understanding what the hottest path in your code was. And it's, well, it's prettier, but it's also a lot more compact. So it puts a lot more information on the screen for you and makes it easy to find. And there are no numbers here. The wider something is, the more important it is, the more prominent it was. On Windows currently, the only built-in tool which generates flame graphs is not Purview. It's the Windows Performance Analyzer. And here's what it looks like. Windows Performance Analyzer is also free, but it's not open source. And its flame graphs are a lot uglier than what I showed you on the slides, but it's still the same idea. I know you can read the text, I can't read the text either. But every rectangle here is a function. And again, the wider a function is, the more time you spend there. And the progression from bottom to top is the call stack, which is kind of makes sense. So when you see something on top of something else, it was called by that function. So you can use the flame graph, you can navigate through the flame graph, and we'd probably get to the same places. So this is compare exchange, and this here is check spelling. Same data, different visualization, which puts the heavy things in front of you, and you don't have to click through trees to get there. I'm only telling you about this so you get envious and to make you want this kind of thing, because Purview doesn't have it yet, and probably will not in the near future, because Vance doesn't believe in it. Vance doesn't think flame graphs are useful. So this is the dictatorship of Purview. Anyways, let's see something else. These were just CPU events. I want to show you slightly different events that can be used for a different purpose. And there's really a bunch of different events that can be used for this purpose. And that's investigating and improving application startup performance. Now, we could talk more about startup performance and what goes into it, but generally, the kind of things you would want to look for to improve startup. First of all, you want to reduce I/O. If you have a lot of I/O in your startup path, if you're loading lots of things from disk, if you're doing lots of network accesses, that kind of thing, of course, it's better not to. So investigating what kind of I/O operations you have is important. Second thing that goes into I/O, into startup performance is just-in-time compilation. When you have a lot of .NET code, it's great, but it also takes a long time to compile. So in a lot of applications, even if the data is loaded from disk really quickly, it still takes a lot of time to compile stuff at runtime. So the JIT has to work really hard. So that's another thing to look for. And of course, you could just have lots of computations in your startup path. Like you might be calculating something, drawing things, filling some caches, maybe that kind of thing, which is just CPU work, which you should also be looking at. So for the CPU work, you already know what to do. Let's take a look at the other two things. My favorite demo of startup performance analysis is Visual Studio, because it's such a lovely, fast application. Yeah. So I'm gonna, I have it in my recents here. I'm gonna run, from Purview, I'm gonna run Visual Studio, and I will check some additional checkboxes. So I want I/O to be recorded. What else? What else? Registry accesses, if I cared. I don't know if I care, but let's record. That should be it. Okay, run. So it launches Visual Studio. This is an Azure virtual machine, by the way, that I'm working on. And it has like SSD storage and many cores. Anyway, let's, and also let's open a solution. I created it today. Yeah, not now, thank you. It's not open completely yet because it's still not responding really. Okay, I think it's more or less loaded at this point. Kind of, no. Okay, there we go. Can I move between lines now? Not yet. There we go. Okay, close. So that was 90-something seconds. Yeah, and it even tells me some events were lost. We'll see how much that is out of all of it. And there are ways around it. I could increase buffer sizes like this suggests. But let's see how many events we had overall. Generally, lost events are not that bad if you only lose a small proportion of events. And looking at the report so far, the 70,000 is nothing, you know? So I had a total of almost 2 million events. Okay, opening the trace. I have the same CPU stacks window still, which I could open. I don't want to. Let's look at other things here. So for example, in the advanced group here, I have things like disk I/O stacks and file I/O stacks. So this is going to open, and I'll do it in a moment, it's going to open the same ugly window, but the data will not be for heavy CPU consumers. The data will be for heavy I/O consumers. So which places in my program caused lots of file accesses or disk accesses. By the way, disk and file is not the same because Windows has a file system cache. So when you access the file, the data gets loaded from disk and goes into a memory cache. So the next time you access that file, it's already in memory. So you might have file accesses without disk accesses. So that's why it's separate. And really, the disk accesses are expensive, the file accesses not necessarily. If it's cached, it's not necessarily expensive, so the cache helps. We also have load stacks for any assemblies we load into the process, which is also interesting because it obviously slows things down. And we have the JIT statistics down here for just-in-time compilation events. Let's take a look at just-in-time compilation first. So this opens a pretty HTML report with all my processes that had a JIT inside, and Visual Studio is the one I care about. And so here what it says, so the total CPU time for that process was 39 seconds. And I compiled 8,000 methods, and I spent 11 seconds on that. So 11 seconds I was compiling, more or less, which is 28% of my time. It's pretty normal for a heavy application to be like that. The more code you have, the more stuff you have to call during startup, the more stuff needs to be compiled. There are ways around it. You can pre-compile, but Visual Studio has some things that are pre-compiled and some things that are not. So this is what it looks like. There is a table which you can open here with all the individual JIT events. So each method separately. That's way more than we want right now. I want some statistics. And so here are some statistics on which modules took me a long time to JIT. And then there's this unknown here, which I'm a little worried about. But let's ignore the unknown for a moment. The second module in terms of JIT time, so this one was 3 seconds, was Visual Studio Workspace VS Integration DLL. I don't know what it is. If I was developing Visual Studio, I might know what it is. But this is costing me 3 seconds of JIT compilation when I launch Visual Studio. The next one is 49 milliseconds. So that's not really considerable. I still don't know about the unknown that's showing there for 8 seconds. I think there was a warning somewhere. Okay, yeah, could not confirm a CLR was loaded. That's not real. Ah, okay, there we go. Background JIT were not collected. I forgot to check a checkbox. I'm not going to repeat that now, but generally, modern .NET runtimes can do background JIT compilation. So your application is starting, and there is a background thread doing JIT compilation at the same time. And so because some of these were not collected, we're not seeing them, I guess, in the report. There's even a warning. It's still interesting, by the way, to collect those background events, but the worst ones are the foreground. The worst ones are the ones blocking your progress. So this is JIT statistics, and if you see any suspicious modules in there, like maybe Visual Studio extensions, you could consider removing them to make your startup a little faster. But this is just Visual Studio. Again, in a typical application, there would be interesting JIT events, interesting in terms of understanding what you're actually running during startup, and also what you might consider pre-compiling to save time during startup. If your JIT time is like 10 milliseconds, great for you, this was not important. But for most of us, JIT time is considerable, and you would want to look into it. So that was JIT time. Let's take a look at another interesting source of slowdown, which is loads, image loads, and assembly loads. So the separation here between image and managed is for native and managed, right? So native DLLs and managed assemblies. Let's look at the managed ones. In the Visual Studio process, of course. There we go. Stacks are broken. Something was a bit wrong here, but anyway. Let's start with the by name tab first. So this just lists a bunch of file names, and I could expand, of course, to see what they are. These are assemblies that I loaded, and you can see like ReSharper being featured very prominently here. So yeah, we had to load a lot of assemblies, and if I want to understand which code is responsible for loading a certain assembly I see here, I can just double click. So for example, this is ReSharper, Profiler, VS integration, whatever, let's see. So this is where it came from. This is the code that loaded it. Now, some things here are folded away, and this time the folding doesn't help us, it hides things. Like these are very high level function. Visual Studio main is very high level. The actual load event is hiding somewhere in here, in this other section. And so whenever you have something like this, you can either disable grouping completely, or you can just right-click, grouping, ungroup. Let's see what it does. Okay, well, it ungrouped a little, so this is still grouped too much. I can keep on grouping like this, or I could ungroup the whole module. And then we get this, which is a broken symbol. That sucks. Let's check another one. Huh, they're all broken like that. I hope not all, really. Some of them are. When you see something like this, it's typically a .NET code which didn't get resolved for some reason. Yeah, no, this is perfectly fine. Yeah, so the folding got confused by this, but there are actual methods here. So, you know, there is this one tiny frame along the way which is bad, and Purview just got completely confused. But you can see everything around it is perfectly legit. So, for example, runtime constructor info.invoke. It's a reflection function. All of us can use it. And if we go down, we can maybe find the original code that was responsible for loading that method. So, you know, just these question marks screwed everything up for Purview, but the data is there. Maybe go back to that JetBrains assembly again and see if we can find what's loading it. Oh, there we go. So these are some JetBrains functions loading solution load task scheduler async something. Again, if I was developing ReSharper, I could understand now why during Visual Studio Startup these particular assemblies are getting loaded. I don't think I actually need all of them during startup, but that's not for me to say. So we can see all the assemblies getting loaded into our process, which is also useful for improving startup times. And finally, just to save us a little time, I will just mention we have similar capabilities for disk and file accesses, like I said. So which files I'm accessing and how long it's taking me. I have similar capabilities for a lot of other events which have call stacks attached to them. So I can tell you what the events are and how I got there from my code. But we don't have very much time, and I do want to talk about a couple of other scenarios as well. So the next demo is going to be trying to reduce memory allocations. I want to show you an application which has a serious GC problem and try to understand where its memory allocations are coming from. Still 100% ETW-based events which Purview can parse and understand. So I'll just run it real quick. I'll run it from a terminal. It's called netallocs. You can reproduce this later. This is what it looks like. It's just a command line tool which is running and just sits there. If I look at it in Task Manager, it's pretty CPU intensive, so it's taking all of one core. And memory usage is not very high, and it doesn't seem to be moving very rapidly in either direction. Let's record its behavior just at a high level and then drill in a bit. So run collect. And I will basically keep the defaults, even removing some stuff I checked before. Start collection. Wait a few seconds. Stop collection. Wait a few seconds. And open the report. Now, I still have CPU stacks here, which I know you are bored of seeing it, but I still have the CPU stacks. I can still tell you where the CPU time is going. We're not going to do it now because your time is too valuable. So instead, let's take a look, just a quick look, at the GC statistics to see if maybe we have a GC problem. Okay, so this is the report coming up. It's an HTML file, as always, and this is my process. And so let's take a look at what Purview tells us. So the total CPU time for that process was 8.6 seconds. and the total GC CPU time was 3.9 seconds. In other words, the percentage of CPU time spent garbage collecting was 46%. Now you could argue that garbage collection is a very useful service, but 46% seems to be a little high to pay for garbage collection. There is actually something even more concerning here. It's a separate metric. Percentage of time paused for garbage collection was 25%. Now it's important to understand the difference. Garbage collection can run at the same time as your process, as your application. But occasionally, it has to stop your threads, do some magic work, and then resume your threads. And so this number here is the proportion of time that the GC actually had to stop your threads completely, so they were not running at all. If this was an application with any kind of user interface, we would probably notice that it was paused 25% of the time. Even if the pauses are relatively small, it's still really concerning. And one final note, which is actually on the optimistic side, the total amount of memory allocated was 7 gigabytes, almost, in, what, 10 seconds or so. So that's actually really impressive. Like, yes, there was a lot of garbage collection, but this program is allocating a gigabyte per second, more or less. You can actually see here, over here, GC CPU milliseconds per megabyte allocated. So that's a little hard to parse, but it tells you that roughly, it took the GC half a millisecond to clean up each megabyte that you allocated. So each megabyte you allocated took the GC half a millisecond to clean up. That's pretty fast. Like half a millisecond is not a long time. So yeah, good job GC, but it seems like we have a GC issue where the GC is allocating, our application, is allocating just way too much. And our heap is not that big. It's 15 megabytes at most. So again, it's not like we have a memory leak and running out of memory. We just have too many allocations in our program. So this is time to enable some extra events. I can go back to collect and just check another checkbox over here, .NET sample allocations. This will record object allocations, not each allocation, that would be too expensive. It's a sampling of some allocations, which hopefully is representative. Start collection. And let's open the report. This one is bigger, but it's worth it. So under the memory group now, I have another couple of reports, and the one I'm interested in now is the GC heap allocations, ignore free, coarse sampling, whatever, stacks. In my Jack compiler process, that's the one I ran. And this is what the result looks like. So again, it's the same window you are kind of getting used to, begrudgingly, but getting used to by now. And it tells you what kinds of things you allocated. This is bytes, this is in bytes, this is in percentage points. Now, unfortunately, all the large objects are just grouped together and called large object. So, and they represent most of my allocations. So if I really care about those, I would just double click. And then I'll see, zoom in a bit, and then I'll see that all of these large objects are really strings, right? And that's almost 10 gigabytes of strings. And you can see where I'm allocating them. I'm allocating them in string concat. Okay, so I'm allocating lots of strings by concatenating strings. That's already bad. I'm doing it in this method, compilation output text writer.write, and I can see what other methods are calling it, so I can investigate the whole stack and see why this method is allocating so many strings. This is out of scope for us. What I wanted to do is find the source location for the allocations. Fixing it is someone else's job now. But again, the sources are online. You can take a look later. I'll give you the link. So we just found the heavy allocation sources in this application. All of what we did so far was based on ETW events, just different kinds of events. CPU sampling events, GC statistics events, object allocation events, JIT compilation events. You know, everything we did was really based just on ETW events and their call stacks. The next thing, the last demo I'm going to show you, is not actually based on ETW events completely, only a little based on ETW events, and that's for .NET memory leak analysis. Because PerfView can do that as well. PerfView can help you understand what your leaking objects are and where they're coming from. So the general process is the following. PerfView has support for capturing heap snapshots. And it has a very sophisticated set of algorithms for capturing a snapshot of your process. I'll show you the end result. It's a lot smaller than pretty much any other tool that captures heap snapshots. And the way PerfView gets there is by removing object contents and doing some smart sampling and removing references that we don't need. There's a lot of work that PerfView does to get a small snapshot which you can still use to diagnose the problem. And the end result is impressive, but we'll get there. Once you have heap snapshots of what's on your heap, you can compare them. And you can see which object types are getting added, which object types are getting removed. And then finally, you can look at objects which are getting added, and you can ask PerfView, tell me what's... And you can ask PerfView, tell me what's keeping those objects in memory. Tell me what roots of references, chains of references, are keeping them alive. Now this process is exactly the same as any other memory profiler. This is what you would do with .memory or Redgate memory profiler or others. But this is something you can actually do in production. So let's see what the process looks like. So let's, I'll use one of my other memory leaking examples. Over here, yeah. So this is an app which helpfully prints its memory usage, just so we know, what to look for. Seems to be going up and up and up. Very good. So let's go to PerfView here, and under the memory menu, I have take heap snapshot, and then I can pick my process, and then I can click here, dump GC heap. By the way, you might find this button useful also. There's actually a lot of questions on Stack Overflow. How can I cause a garbage collection in my process from the outside? So this is how. It actually only works in .NET 4.5, but good enough for me. So let's click dump GC heap, and it created a snapshot. It took, I guess, less than a second to create. And I want to show you the snapshot itself, what it looks like on disk. Oh, I just closed the app by mistake. Right, so let's do it again, sorry. Just grab another snapshot of it. Dump GC heap. Okay, ooh, exceptional condition. Directory, what directory? That was weird. Anyway, let me show you the file real quick. PerfView, net leak, right? No. Sorry, PerfView netallocs. And yeah, for some reason I put the dump file here. So this is the one, memory leak 1 GC dump. 158 kilobytes, that's the heap snapshot. Now, just for comparison, I'm going to go ahead and capture a memory dump of the process from Task Manager. This is a full memory dump, and it is here. And then I'm going to go back to perf_view and generate another snapshot. And that other snapshot is 470 kilobytes, while the dump file is 104 megabytes. So just to get a little perspective about how potentially useful this can be. If you have a large process with a lot of memory, generating dumps and then opening them in a debugger, or generating dumps and importing them into some kind of profiler, it might work, but you can expect really big files. The GC dumps, the GC snapshots produced by perf_view, they don't have all the same information, but they usually have enough to diagnose the problem. And again, they don't have the object contents. They don't have a lot of useless stuff, like they don't have thread stacks. But you don't need thread stacks to see what's on your heap. So it's kind of reasonable. So you're not giving up a lot, and you get those snapshots, which I can now open. So here they are, memory leak 1 and memory leak 2. This is the one from the first one. So these are the two I want to open. Familiar window. Except this time, you know, at least he changed the tab titles. I don't know if you noticed, but previously it was like col3, and now it's ref3. So that's a big improvement. And it's showing you the biggest types you have on your heap. So this is request and response. It's a very, very simple example. So request and response, you can see their sizes just out of the screen here. So this is 21 megabytes, and this is 2 point something. This is 2 point something megabytes. And let's take a look at the other snapshot I have. Second one. So here, is it the same process? No, that's from the previous run. This one looks a bit broken, honestly. Let's try another heap snapshot. It's still running though. Okay. Let's see. Yeah, that makes a little more sense. So again, here are request and response. I have 150 megabytes of request and 115 megabytes of responses. Well, in this case, it's pretty clear visually what the difference is, but perf_view actually has this amazing diff capability, where you have to open both windows first, and then you go to the second one, and then you can diff with the first one, which is a very reasonable UI, right? And that opens the diff view. And so if you look here, the numbers, in this case, they're all positive, but they can actually be negative as well. So it's now showing you just the diff between the types. So you can see I have an extra 129 megabytes of requests and an extra of 13 megabytes of responses. So this is the second step of our analysis. We now have a pretty reasonable idea of what objects are growing in memory. And that was relatively cheap, those snapshots. Lastly, I want to tell you what's keeping those objects alive. So I double-click them and see a reference path. Again, this is a familiar window. It's the one that's used for a call tree, usually with methods. But this time it's not methods, it's types and objects. And what I can see here is that my request objects are actually held by my response objects. Maybe makes sense. My response objects are held by a list of responses, and my list is held by a static variable called responseCache._cache. So I have a static variable which has a list of all my responses that I ever created, and my responses have... That also happens. But my responses have requests inside, and so it goes from there. Now, you might ask one other thing, which is also an example of perf_view's capabilities. This is the number of instances, 25,854. And this is the size in bytes, 129 megabytes. So these are pretty big objects, right? They're like more than a few kilobytes big, which is weird. I don't know, I mean, you need a lot of fields in an object to make it a few kilobytes, right? The only objects you typically see that are a few kilobytes are arrays or strings, right? That kind of thing. So it turns out that helpfully, Purview folded away some types for us. If you look up here at the fold patterns, it's folding away any arrays and any strings. Because usually you have a lot of strings and a lot of arrays and you don't really care about them. So showing them to you would be a waste of your time. So instead, Purview just adds their sizes into the object that references them. So the requests are not really that big. If I remove the folding and go to the previous screen, we will see that actually most of my heap is in byte arrays. And if I open the byte arrays, this one. If I open the byte arrays, you'll see, yeah, so the byte arrays are referenced by requests, which are referenced by responses, and so on. You see the full chain. This is another useful feature, and it's actually useful not just with strings and arrays, it's also useful with your own types, which for you are not interesting. I don't care about this object, it would only clutter my view, just fold it into its parent, just show me the parent object instead. Very simple functionality, which is actually common across all the types of windows we saw. You can do the same thing with methods. This method is a library function, I don't care about it, just show me the color instead. This is something you can do as well. Very simple. So this is some of what Purview can do. I'm sure if Vance were here, he'd say, like, this is just scratching the surface, let me show you the really cool features now. But I think these are some of the key scenarios that I use Purview for. It can be used as a profiler. It can be used as an allocation profiler as well. It can be used for memory leak analysis, or at least understanding what objects you have on your heap. So there's a lot of things you can do. And yes, it can do more. And it has a user guide, and it has a GitHub repository that you can take a look at and even contribute. So it's a really powerful investigation tool. It doesn't work for every situation, but there are many situations in which it helps, is what I'm saying. So ETW really, to wrap things up, ETW really is the #1 go-to tool for Windows performance investigations, and Purview for .NET developers, for .NET applications anyway, is one of the better ways to use ETW on Windows, especially in production, when you can't afford any of the more commercial heavyweight tools. And it's definitely possible to run profilers in production. It's definitely possible to investigate memory leaks in production. You don't have to copy the whole environment over to your computer to do these kind of tasks. So I'm done after 75 minutes, like I promised. But if you have questions, I'll be happy to answer. You were very quiet during the presentation. If you'd like to chat to me privately, I'll be here as well. So let's maybe start with if anyone has questions for which they don't mind everyone to hear. Yes?
I have a question. About button for GC. What generation of GC it was?
Full GC, all the generations. Yeah. It actually is also based on ETW. So the ETW in recent versions has like bidirectional commands. So the controller can actually send the provider commands, and they use that. Yes?
What if I want to profile .NET Core application on Linux?
Right, so profiling .NET Core applications. I'll start by answering the question you didn't ask. So you can use Purview to profile .NET Core applications on Windows. .NET Core is more or less the same, and the ETW events are the same, and everything is the same. On Linux, the story is different. I could do a different talk on profiling .NET Core on Linux. In fact, I have. You can find the talk I did at NDC about profiling .NET Core applications on Linux. The Microsoft official workflow is actually to use Purview, but you can't run Purview on Linux. So what they have is the script, which you can run on the Linux machine, It collects a lot of information, and then you can open it in Purview. I don't think it's a really good way of doing things, so I have my own opinions, and my talk has some. But the Microsoft official way is to still use Purview, you just have to collect in a different way.
And ATW is available on Linux.NET perhaps.
ETW is event tracing for Windows, so it's not available on Linux, but the events are available. So Microsoft, on Linux, Microsoft are using a different framework to produce the same events. So you can still record garbage collections or JIT compilation, but you use different tools.
One question. I didn't understand how accurate the memory snapshots that we
How
take.
what? How what?
How accurate? So it's accurate. So you said that we throw away all the things.
Sorry, I just didn't understand what you said. Yes. So what do you mean how accurate? Keep explaining.
I mean, so we in this snapshot we can see all objects.
Right. So let me open that window for a moment again. So what happens is, first of all, you have the option of suspending the process while the snapshot is taken or not suspended. By default, the process is not suspended, which is great. I mean, the process keeps running, you're getting your snapshot, everyone's happy. It means the process keeps allocating objects and keeps getting rid of objects while you are collecting the snapshot. So the snapshot might be inconsistent. There could be some objects in there that already got removed, and there could be objects that got added and you don't see them yet. So it's not really a snapshot in time. It's usually good enough because the changes are small, but if you really want something more accurate, you can suspend. You can click this freeze checkbox and then it will stop the process, record, and then resume. So that's one thing. The other thing is this maximum value over here. So there is a limit, by default 250,000 objects, that Purview would like to put in the snapshot. It first goes over your heap. If you have more than 250,000 objects, it will do smart sampling. So it would remove some objects, and it would try to do it in an intelligent way so that ratios are maintained and reference chains are represented. It's a whole bunch of code he has for that purpose. You can increase this. So if you have 5 million objects, the snapshot would still be reasonably small, so you can just change this number. If you have like 50 million objects, it would take a long time to create a snapshot, and then you might want to use sampling in. So this would give you not all the objects, just a sample. Again, in theory, the sample could be far away from reality, but in practice, it's usually pretty close. So if you have a reference chain which is responsible for 50% of your memory leak, then you will remove it, and it will only remove 40%. It's still something. But in theory, if you do sampling, it's not going to be accurate. But if you have less than this number of objects, it's going to be all the objects. It's going to be completely accurate. Yes?
First of all, thanks for your talk.
Thank you.
It's informative and interesting. Here's a question, and then somehow I think it's the opposite of the question that was previously asked. You showed us lots of examples where some heavy memory allocations or some heavy performance problems could be monitored and discovered using Purview. But I think there are cases when your performance monitoring using Purview may hide actual problems. Like what key zones, what we should do with Purview monitoring essentially to things that will clash with our problems and will hide the actual problems for us.
How to what? Sorry, what's the last part?
Yeah, the question was what things that we should do if which could hide the actual problems for us.
Which would hide?
Hide the problems, like we monitor something and we see nothing, but then we disable the monitoring and then the problem persists.
Yeah, so again, that's something that can definitely happen in theory, but one of the advantages of ETW is that it is very non-invasive. So it's not, it's not injecting things into your process. It's not changing your configuration. Basically, what happens is that the provider is calling the Windows API anyway, and then when you enable the provider, the Windows API just decides to write that data into a memory buffer. From the side of the provider, it is a very, very low overhead thing, because basically it's just putting a bunch of data in a shared memory section, which is not even synchronized because it's per CPU. So, in terms of performance overhead by enabling providers, unless you enable too many providers, the target process will probably not notice. But, I mean, any kind of monitoring changes the system a little. So when you turn on ETW, there's a certain amount of memory reserved for the buffers. So, you could suddenly get memory conditions that are slightly different. The provider itself, Purview itself, takes some CPU. Logging the events to a file creates disk I/O. So it's all there. Thing is, there's not really something even more lightweight if you need the individual events. If you just need some kind of aggregation or something, you can build tools, not Purview, you can build your own tools, which use the ETW API and do real-time processing without files. And then you can get even lower overhead because you're just operating with that shared memory buffer. So if you don't need the individual events, you can do that. I have a couple of open source tools that do real-time processing. But there's really not a lot of more lightweight things you can use. That's basically the answer.
I have one question.
Choose first. Let's do it in order. Yes?
It's interesting to collect information when something went wrong, and can you works in some waiting mode and when something.
Excellent question. So yeah, basically triggers. Can you trigger recording? So if you look at the command line help for Purview, and of course I'm not going to show you the whole thing, but you can look later. So Purview has, scrolling down a little, lots of command line options. But specifically, Purview has all these triggers which can be used to start and to stop recording. So for example, you can stop recording when a certain performance counter is greater than a certain value. So when CPU usage is over 80%, start recording. You can also have time limits. So you could start recording for 5 seconds, then stop, that kind of thing. The triggers include a bunch of stuff you can take a look at later. If it's not enough, then you can build a wrapper which would monitor the event and then launch Purview. But for a lot of scenarios, Purview actually has it built in. Yeah. There's even something really nice for web applications. It's here, stop and request over milliseconds. So whenever there's a request in IIS longer than something, give me a recording.
Can I see executing scripts in database like Shopper?
Can I see the scripts?
Can I see executing commands for the database?
Okay. Yeah. So it depends if the database has ETW events with the command text. I don't think SQL. No, I don't know. SQL Server has an ETW provider. I actually haven't looked at the events because SQL Server has a bunch of other monitoring tools which DBAs usually use instead. But it's absolutely possible that SQL Server has ETW events for commands being executed. It wouldn't surprise me. For other databases, third party, not Microsoft, you'd have to check. Just open the provider browser, point it to the process, and see what providers are. So in theory, yes, it would be nice with it, but I don't know for sure. Okay, yeah.
Just one question.
Sure.
The EATW and Windows performance counters, I think it's two similar things. Why there is two ways for doing same things?
Yeah. So Windows performance counters, just to tell everyone if you don't know, Windows performance counters are very simple numeric sources of information about things on your system, like CPU usage per process or heap size in the garbage collector, so it's just numbers. So really, it's similar to ETW, right? But it's a lot less because it's just numeric information, and it's not really push-based. So the way performance counters work is that I, as a provider, write some piece of data to a shared memory, and you read it from there when you feel like it. So there's no push model, there's no buffering. It's more a monitoring tool, not really a logging tool. And it's very, very limited in scope because you only have numbers in there. But then you ask why even have performance counters if we have ETW, and the reason is ETW only showed up in Windows 2000, and Windows was around for like 15 years before that. So that's why. Performance counters, well actually I don't know if there were performance counters in Windows, the non-NT Windows, but Windows NT had performance counters from the start. So that's at least 93 or so. So for a few years, we only had performance counters. But today, there's still uses for performance counters because they're very, very low overhead. You don't need to turn on anything, you just read from memory using perfmon or something, data that's already there. And for ETW, you have to turn on events, they log them to somewhere. It's a tiny bit more expensive. So that's, yeah. I mean, if they built Windows from scratch now, maybe they would decide differently, but that's how it is.
Sometimes users server applications and high usage of some function or methods is quite normal. Would I find anomalies when I have two samples, or first sample is collected when application worked normal, and second sample when application has some performance issues?
Yeah. So first, just to make clear, we are not recording every function, right? Where we get samples of, of what the CPU was running. So in theory, you could have a function that did something and it wasn't on any samples because it was between. But given that, any two reports you have in Purview, you can diff them, not just the memory reports, the CPU reports as well, the file IO reports. In fact, you can take two unrelated reports. You can take a stacks report and a file report and diff them. It wouldn't be very useful, but you can. It's just general diffing, really. And then, yeah, it would show you if any functions got weird. But for that to happen, they would need to be sampled. And again, smaller, very small things that don't take a long time might not be sampled. Okay. So, if anyone has any more questions, please feel free to approach. I'll be here for a few more minutes. And also, you can definitely get in touch. On Twitter, I can also put my email in here. I generally don't like putting it on slides because they end up on the internet, but then this doesn't really work. But then if you'd like to reach out, please just shoot me an email. You can find the slides up there. And I will also post to my Twitter account the demos I've used if you'd like to take a look at them. But mostly you just need Purview and to start experimenting a little. Purview comes with a little built-in tutorial. And there's videos online. And really, if it's something you haven't used before, I very much recommend that you at least give it a try. So yeah, thank you very much.
большое. Очень интересный доклад. Так, я напоминаю, что мы ищем докладчиков на нашей встрече, вот, поэтому если у вас есть что рассказать, может быть, проблемы, с которыми вы столкнулись, как вы их порешали, может быть, что-то интересное нашли. В общем, мы всегда открыты для вас, заявляйтесь, и, может быть, на следующем этапе кто-нибудь из вас будет докладчиком. Давайте еще раз поблагодарим Сашу.